Every web page, API call, and digital transaction you execute relies on a single protocol. HTTP, or HyperText Transfer Protocol, is the application layer foundation that underpins every distributed, collaborative hypermedia system in the world. This diagram shows the standard TCP/IP networking model. Data moves from the physical hardware at the network interface layer, routing upwards to HTTP at the application layer. Once there, the default channel for unencrypted HTTP traffic is TCP port 80. HTTP processes billions of requests per second globally. It achieves this scale through two deliberate design constraints. It is entirely agnostic to the data formats it carries, and it is inherently amnesiac regarding the connections it makes. To understand how these constraints operate, we will map out HTTP's network topology, parse the strict formal grammar of its text messages, and define the mathematical semantics of its methods. Grasping these mechanics is essential for any network engineer. We are analyzing how deliberate architectural limitations enable global-scale distributed intelligence. This schematic shows the core interaction model of HTTP, a request-response protocol between two distinct nodes. The node on the left is the user agent, the sole initiator of any transaction. On the receiving end is the origin server, which holds the requested digital resource. Between endpoints, requests pass through intermediaries like proxies, gateways, or tunnels. Regardless of the routing path, HTTP enforces strict statelessness. Once an origin server delivers a response, it immediately discards any memory of the client's identity or previous connections. The engineering consequence is significant. Without persistent memory on the server, the user agent is required to rebuild and transmit the entire necessary context from scratch on every single subsequent request. Because transmitting this redundant context introduces network latency, HTTP relies heavily on local caching mechanisms to store previously fetched resources and prevent unnecessary repeat trips across the network. Forcing the client to bear the burden of state management frees the origin server from the memory overhead of tracking thousands of active sessions. This specific, calculated architectural trade-off is exactly what allows a single server to handle millions of disparate, concurrent network requests. To see how those requests actually execute, we must look at the raw ASCII payload exactly as the network stack reads it. Every HTTP message follows a precise grammar equation. A request start line requires three variables: the method, the URI, and the protocol version. A response mirrors this, delivering the version, a status code, and a reason phrase. Below the start line sits the message header section. This is a sequence of MIME-formatted key-value pairs that supply critical metadata about the transmission, the requested resource, or the client environment. The parser reads this text linearly until it hits an absolute boundary. A double carriage return line feed, or CRLF, acts as the hard delimiter. This invisible blank line tells the machine exactly where the headers stop and the actual payload body begins. While HTTP 1.1 relies heavily on this raw text parsing, modern updates like HTTP 2 take this exact same semantic data and compress it into binary frames to increase transmission speeds. This reliance on a rigid, unforgiving text grammar guarantees universal interoperability. Because the parsing rules are absolute, an embedded microchip can seamlessly format a request and communicate with a global enterprise mainframe. The first variable in that request syntax, the HTTP method, is not an arbitrary command. Each method is governed by strict mathematical properties that dictate how it interacts with the server's state. Get and head are secure, read-only operations that don't alter server state. They are also idempotent, meaning repeated requests yield identical states. Put is idempotent but not secure, safely overriding files. Post breaks both rules. Repeated requests continuously generate distinct new records, mutating state. For resource management, the delete method is the dedicated semantic command used specifically to remove a specified resource from the web server footprint. Conversely, the head method exploits its secure and idempotent nature to perform lightweight reconnaissance. It requests only the headers of a resource, allowing a client to verify a URI's validity or check cache coherence without paying the bandwidth cost of downloading the full body. System architects rely entirely on these semantics. Strictly mapping operations to their correct method properties, like never using a GET request to delete a database row, is the mandatory foundation for building fault-tolerant, predictable network architectures. Beyond managing state, HTTP derives its flexibility from its format agnosticism. It acts as a carrier signal, completely decoupled from the actual data payload it transports. HTTP achieves flexibility via MIME encodings, using the content type header to classify payloads. Because early systems only processed basic ASCII text, complex binary files must be wrapped in encodings like base64 to safely survive the trip across these text-based protocols. Because of this risk of data corruption, the content type and content length headers are the two mandatory entity headers required in any HTTP message that includes a payload body. Other critical headers handle routing and tracking. The host header allows a single IP address to serve multiple distinct websites simultaneously. Meanwhile, the referrer header tracks the exact origin URL that directed the user to the current resource. Once the transmission is processed, the server replies with a precise numerical status code. These are grouped into 5 distinct classes: 100s for informational, 200s for success, 300s for redirection, 400s for a client-side syntax error, and 500s when the server itself experiences an internal failure. By forcing metadata into structured headers and using MIME to isolate the payload from the transport protocol, engineers decoupled the delivery rules from the content types. This decoupling allowed HTTP to natively transfer high-definition video and distributed objects that didn't exist when the protocol was first drafted in the 1990s. A request originates at the user agent, armed with strict syntax headers. It travels through the transport layer, bypassing tunnels and proxies, until it locates the origin server on port 80. The destination machine parses the CRLF boundaries, executes the requested semantic command without mutating unauthorized state, delivers the MIME-encoded response, and immediately purges the interaction from its memory. The entire web stack remains built on this exact sequence. HTTP has maintained its total market dominance precisely because these layers are so rigidly decoupled. The system works not because of what it retains, but because of what it discards. Its forced amnesia, its mathematical method semantics, and its blind transport mechanics are the defining architectural principles that permit the HTTP protocol to function at a global, planet-wide scale.